So as we think about the engineering that is now marrying biology, a lot of it is would be considered to be nanotechnology, and we're fortunate to have one of the world nanotechnology experts with us in Sangeeta. So you want to talk to us a little bit about what you see as the opportunities in nanotechnology, particularly in this bio-nano world.
Sure, yeah. Hi, everyone. It's great to be here with you, Susan.
Pleasure.
Yeah, maybe so just to set the stage, as Susan said, I work on nanotechnology, and this should be a familiar image. It's a microchip inside each of your smartphones. And you'll know that, nowadays inside a smartphone, there's about 12 billion transistors on this footprint. 50 years ago, that was one transistor on the same footprint. And that aggressive miniaturization was really motivated by the interest in speeding computation and making it portable. And we're going to talk a lot about AI over the next couple of days, and all of the things that we think about with generative AI are in fact enabled by the speed of computation. So that's kind of what's been enabled on the software side. But what I want to talk about with Susan over the next few minutes is really the hardware side. So the miniaturization on this silicon chip has been enabled by material science and physics, thin film deposition, and light-based patterning. And the nodes on this chip are now 5 nanometers in size. So we can make materials that speak the language of biology, that are the length scale of molecules, DNA, RNA, proteins. Single receptor is 10 nanometers. And maybe just to make the point a little more concretely, nanotechnology, when applied to medicine, is this new emerging field of what we think of as nanomedicine. And these are 3 examples from COVID that may not be on your radar as nanomedicine enabled, but they are. So the variant sequencing that was done was nanopore enabled. The lateral flow assays, the paper diagnostics, the colored strip is structural color in gold nanomaterials. And of course, mRNA packaging and lipid nanoparticles, we'll hear a lot about that over the next couple of days. Again, that was nano-enabled, and those are really long-standing investments, as Pablo described earlier, by largely government investments in nanotechnology. So it's an incredibly exciting time, as we showed on the first slide, because all of these things are coming together to allow us to solve, unmet needs for our patients in brand new ways.
Yeah. So when you look at just the budget around healthcare in the United States, we spend something on the order of 18% of U.S. GDP on health or healthcare, and I make a joke actually that I learned from Sangeeta. We could call it healthcare, but it's probably more appropriate to call it sick care, because we wait until people are pretty sick before we intervene. And the question is, how do we actually bend the curve on this kind of spending and actually bend the curve on people's experience of disease and the success in dealing with disease? And I don't need to tell anyone here that the best approach to beating disease is by prevention. And when I give this talk to a lay audience, I remind them that it's important to get all those vaccines that prevent you from getting the diseases that we hate. And even in the realm of cancer, that as we develop vaccines against the perpetuator, the organisms that lead to cancer, that'll get better and better. But the fact is, if we do all the preventions you're supposed to, if I wore the sunscreen I'm supposed to be wearing, if we stop smoking, and the reduction in smoking has had an enormous effect on reducing lung cancer. But what we need to do is get better at diagnosing disease earlier. We have what I call diagnostics deficits, and nanotechnology, nanobiotechnology presents incredible opportunities around being able to actually deal with the diagnostics deficit. And Sangeeta is always my hero, so when I say this, and I'm speaking by myself, I have to describe it, but happily, Sangeeta can speak herself to some of the incredible approaches now available around earlier diagnosis, which really opens the opportunity of reducing the cost and the impact of sick care.
Yeah, great. That's a great setup for the need for early detection. And one of the things that I also have a slide, because it's very hard to describe without pictures.
You could wave your hands around.
That's true. I can do that, and I'm happy to. One of the things about nanotechnology, which has been really an interesting evolution, is when it started in the field, we were fascinated with the nanoscale physics. So what happens when you shrink a material down to the nanoscale? So you take gold and you make it small and it turns the color red. And it can be excited with electromagnetic fields and heated depending on its size and shape. There's all these interesting physical things happening at the nanoscale. But what we learned as a community in nanomedicine was that the way materials traffic in the body is also size dependent. And that's what's on this chart behind me. If you inject a nanomaterial in the body, in the bloodstream, largely it will be taken out by the liver and the spleen, because the liver and the spleen's job is to take out particulates. If it's small though, if it's smaller than 5 nanometers, the kidney is a filter. It's a 5 nanometer filter. And so those materials will pass right out. If you have diseases like solid tumors or diseases of the brain, you can get into those organ systems in certain size windows, in this case about smaller than 100 nanometers. So it's a very fascinating mapping beyond the nanoscale physics. Now we have nanoscale biology, and this allows us to invent new things. And I want to give you 2 quick examples that turned into startups out of MIT that used this observation. So one of them is a size switching material. So these are materials that are about 20 nanometers in size. You inject them in the bloodstream. They can be activated by enzymes in the tumor microenvironment, and the enzymes in the tumor microenvironment clip surface molecules off that nanomaterial. And those surface molecules, now smaller than 5 nanometers, come out in the kidney and get concentrated into the urine. That becomes an ultra-sensitive enzymatic detector for disease. We spun out a company called Glimpse Bio that looked at diseases like NASH and now HCC, early cancer detection for liver disease. So that's one example of a nanoscale property that can be exploited to create a whole new class of what we call synthetic biomarkers. Make your own biomarker for your disease of interest. Another example, since this is an innovation conference, is a brand new study that we put on bioRxiv just about a month ago with the Broad Institute, with Victor Edelsteinson and Chris Love. And this is an example of liquid biopsy for circulating DNA. This is something that you've all heard about. Instead of taking a biopsy of a tumor, you could take a blood draw and you could look for mutant molecules in the blood. And this technology has been really exciting. But the challenge has been finding enough molecules in early cancer to really deliver on the promise, to make it sensitive enough for early cancer detection non-invasively. And what Victor and we realized was that the DNA circulating in the bloodstream, the cell-free DNA circulating, was in fact a nanoparticle. It's an 11 nanometer nanoparticle. It's the nucleosome, histones, wrapped in 166 kb of DNA. So all of the DNA circulating is a biological nanoparticle. And when we realized that, we realized, guess what? The liver takes it out. And if you pause liver clearance, you get a 100-fold boost in cell-free DNA. So that's a second company. We're just spinning it out. It's called Amplifier. But those are just some ways that nanotechnology and unmet needs of medicine can kind of come together. And I really want to credit Susan for recognizing that these conversations should happen, because you built a building when you were president to make this happen.
So let me just say so what these biological marvels that Sangeeta has described, figuring out actually that nature's got tricks up her sleeve. Nature's genius is and putting nature's genius together with engineering has been incredibly productive. So at MIT, when I arrived at MIT, and I was spending a lot of time listening to the community about what their dreams would be, and I would always ask people what were MIT's opportunities and responsibilities in terms of the next decade or so. And I heard again and again the opportunities around the convergence of disciplines. Every academic organization of a sufficient size is organized into departments and schools, and frankly, those often end up to be silos with concrete barriers that prevent people in various subtle ways or overt ways from collaborating. And I heard from Tyler Jacks when I asked him, who was then head of the Center for Cancer Research, about this incredible new activities going on, merging engineering with cancer biology. there was a lot of enthusiasm for that. And happily at MIT, we had an organizational structure that allowed us to pull people together who had similar research interests, but came from different disciplines. So we activated that in the building that's shown here in the upper left, which is now the Koch Institute for Integrative Cancer Research. And the Koch Institute houses about half engineers, half cancer biologists, and beyond that, there is a handful of clinicians thrown in because we really want to. Our goal was to attack cancer not just in a laboratory setting, but actually with impact for patients. So the Koch Institute was designed to optimize collaboration. In that little map of one floor, we show the engineers on one side and the biologists on the other. That was generation one. Generation two, as people have left and new people have come, has mixed up those colors even more. I make a joke about that middle beige part. That's where the stairways and the elevators and the restrooms are. So you cannot go through your day without running into someone who is from a discipline that's different from your own. It has been immensely, immensely successful in terms of accelerating the kind of work that Sangeeta has just described. And our clinical collaborators have been as enthusiastic as our scientists and engineering collaborators in making this work. Within the Koch Institute, there are some subdivisions. Sangeeta is the director of the Marble Center for Cancer Nanomedicine, which again, she's described a couple of the innovations coming out of that. But you can see from the map in the bottom right, where the MIT campus is shown in the dark red, the Koch Institute, the position of that is shown in the K, kind of in the middle of it. And then the rest of Kendall Square surrounds us, and you probably can't read the names of all of the companies. There are, I don't know how many companies now within walking distance of the Koch Institute and the MIT campus. Our colleague, Phil Sharp, who was an early proponent of this kind of idea of taking biological insights and turning them into companies, founder of some of the very early and great biotech companies, has a great saying. He says, technology travels on 2 feet. And indeed, you can walk out of the Koch Institute, walk across the street, and find some collaborators from industry who have been very, very interested in picking up our techniques. So,
maybe
go ahead.
just to jump in.
Yeah.
I mean, I can say as an inhabitant of the building that you helped build, visioned. Some of the magic, I think, of the community is that the inventors need safe spaces for invention. You need a place where there are colleagues that you like and trust, where nobody really knows what they're talking about. You just get to sort of imagine the future, what if we could do a breathalyzer for that? And there's a clinician down the hall and an engineer over there. And so what works, I think, what's really special about this building, and I think it's a template for other ecosystems, is that there are these sort of nested communities. So this is the nanomedicine community, but there's lots of other communities. And then, of course, as Susan has described, we're within Cambridge, and so you can get an investor, or you can get a pharma collaborator, and so on. So it's a way to sort of strengthen the biotech ecosystem, Pablo, that you were referring to. And it has been incredibly productive. So this is just one example, I think, of the companies that have come out of the Koch Institute over the last few years. So in the last 10 years, I think we counted it was 110, but 130 since the beginning. So this is an incredibly fruitful endeavor for inventions and then starting the journey to patients, which is really the role for biotech.
And I would say that we've picked up on a theme that has been part of MIT's founding ambition, which was to get not just great science and technology insights, but actually get them out so that they can help improve the condition of the world.
Yeah, and acceleration, which is, I think, the theme of this conference. How do you go faster?
So in the last few minutes, we want to talk about a deficit that we want to close. And Sangeeta was, again, the founder of this, as well as her companies. And thinking about, all of our faculty and all of our students having a chance to participate in this incredibly exciting enterprise. And we discovered that, well, not so much, right?
Yeah. Yeah, so we did a study together with Nancy Hopkins, who's really the gender equity pioneer here at MIT, looking at life science startups across 7 departments that tend to start biotech companies here at MIT. And we found that the women faculty start less than 9% of them, and they're underrepresented on scientific advisory boards.
The women faculty being about 25% of the MIT faculty now.
Indeed, yeah. And they're underrepresented basically in the ecosystem. And Susan, you've coined this term, which I love, which is sort of there are hidden network effects, right? So they don't know when they have an invention who to call, how to get funded, where to begin. And we calculated that the women faculty here at MIT, had they been starting companies on par with their male peers, there would be 40 more companies, 40 more medicines.
And there is nothing I hate more than squandered assets. And the fact that these women have not started the companies means that there are drugs and there are therapies that we don't have today because these women don't have the opportunities to actually turn their great discoveries into companies that deliver solutions to our patients.
Indeed, so we're hacking this. You're gonna hear about hacking, MIT's tradition of hacking. We've written about it, we have lots of data, and we're doing experiments. We started something called the Faculty Founder Initiative. Last year, we ran an incentive prize competition for 9 women faculty, $250,000 prize. We welcome contributions. And actually 8 of those 9 women are now starting companies after a 6-month stint. And importantly, we're creating a cohort of those women so they can help each other and pay it forward. So that's just one, I think, opportunity. There's lots of opportunities for acceleration.
There are, and I think this, an event like this actually brings people together in ways that perhaps we haven't gathered before. To really move these ideas faster, into the marketplace. So there's the marketplace, there's the clinic, all kinds of ways to do good and expand our reach. So I want to thank Jim and Pablo for bringing this ABI to MIT. It's a great pleasure to be with all of you, and it's going to be an exciting couple days.
Yeah, of acceleration. So thank you.
Thanks, everyone.